Welcome viewers to the fourth lecture for the online series of lectures for the course of General Relativity. In the previous lecture we had a detailed discussion on tensors, objects which belong to a vector space that we denoted by TPR, S, situated at each point P on the manifold M. Okay, and how these objects transform under coordinate changes. We also saw that in the previous lecture. Recall from the previous lectures as well that a tangent vector at a point P on the manifold M is just a map X restricted at P from C infinity M comma R to R, where C infinity M comma R is the space of smooth functions, real valued smooth functions on the manifold M. Okay. So that is X restricted to P acting on F is a number, since it belongs here, is a real number. For a given function f in C infinity M comma R. Okay, good. Now, so this is the story of the tangent vector X restricted at P, and the vector field on the other hand, a vector field X on the other hand is the map X from C infinity M comma R to C infinity M comma R. So in some sense this vector field X is an operator which takes a function to another function, given by xf. Okay, xf if for a given f in C infinity M comma R, meaning that f is a real valued smooth function on the manifold M, then xf is supposed to be another function here in the same space, real valued smooth function on M. So xf is a function, and this evaluated at P is supposed to be a number. Function evaluated at a point should be a number, and this number is defined with the help of the tangent vector like this, because we already know that X restricted at P acting on F gives a number, and they should be the same. Okay. So therefore we have just seen that xf is a smooth function on the manifold because it belongs to this space on the manifold. That is, xf is a function that acts on P, a point on the manifold, to split a real number, which is x at P acting on F. Okay, good. Now we also saw that, well, we studied the tensor R comma S tensor in the previous lecture, which are objects belonging to vector space, this calligraphic T sub P R comma S, which we saw earlier that is a vector space of dimension n to the r plus s, where n is the dimension of the underlying manifold. Okay, so at each point P of M, we can have a vector space of dimension n to the r plus s, where these tensors belong. Okay, so T restricted at P, they are vectors belonging to these vector spaces at each point P on the manifold M. We have seen it earlier. Now, an R comma S tensor field. Okay, you see the analogy? We started our discussion with tangent vector, and then we looked at vector field. Okay, now we are talking about tensors that we studied in the previous lecture, and now we are trying to define tensor field. Okay, so an R comma S tensor field is a map T, okay, that maps any point P in M to an R comma S tensor T at P. Okay, so let me create some space for me here. So what we have just seen here is that T is a map that is going to map P to a tensor T at P. Okay, so now given R one forms, we discussed what one forms are in the previous lecture in detail. So say we have R one forms, eta 1, eta 2, all the way up to eta R, and we have S counterparts, meaning that we have S vector fields, dual counterparts of these one forms, x1, x2, all the way up to xs. Okay, now we can define a function. Given R1 forms and S vector fields, we can define a function. We can define a function T that will act on these R1 forms and S vector fields. R1 forms and S vector fields. Okay. So this is the function. The whole thing is a function. Okay. We are defining this function that will take a point on the manifold to the set of real numbers. How this is defined, let me show you by So if I choose a point P on the manifold M, that is going to spit out this number, the number that we get out of this function in the following way. T at P is a tensor at P, okay, R comma S tensor at P, and that is going to act on R covectors by restricting these one forms, each of these one forms to the point P. We are going to get a covector. So if we restrict each of these R forms to the point P, we're going to get R covectors, right? So these are the R covectors. Sorry, this is P. It R at P, and we are going to restrict these vector fields to the point P. So x1 restricted to P is going to give us a tangent vector, or just a vector. Then we are going to get x2 at P, which is a tangent vector again. So we are going to have S such tangent vectors. Okay, so the resulting thing here is a number, right? Because this is an R comma S tensor, and this is acting on R covectors and S tangent vectors to spit out a number. And this number is defined by this. Okay, this is how we are going to define a function, this function. Okay, so the tensor field T, we call T the tensor field. The tensor field is going to be smooth if this function P drag to this number. Okay, if this function is smooth, okay, this function is smooth, then we are going to say that the underlying tensor field is smooth. Okay, so in other words, we can write this function as follows: T eta 1 eta 2 eta r comma x1 x2 xs is a function. That function acts at point P of the manifold M to spit out a number, and that number is nothing but this number. T at P, the tensor, R comma S tensor acting on R covectors, and S tangent vectors. S tangent vectors. Okay, good. Okay, let me erase everything now. Now we are going to introduce the notion of commutator between two vector fields. It's an important notion. The commutator of two vector fields is again a vector field. That is, so we are going to denote the commutator of two vector fields by this bracket between x and y, and this is a vector field. We're going to see explicitly how they are actually vector fields. Given two vector fields x and y. Okay, in fact, if you have x and y, they are two vector fields on the underlying manifold. Their product is in general not a vector field. Okay, but if you write this commutator of the vector field as the product xy minus yx, then this is going to act as a vector field that we will see. Okay, so this is how we are going to define x, the commutator of x and y. This acting on f is going to be a function, right? If x comma y, the bracket of x comma y is a vector field, right? This is going to be a new function, right? So this is how, so according to the definition of the commutator that we have here, this is going to be equal to x y f, right, minus y x f. Okay, so this is going to be a function y acting on f, right, because y is a vector field. So since f is a smooth function, real valued smooth function on the manifold, y of f is another function, and x acting on that function is again a function, right? So this is a function, okay, and this guy is again a function. Okay, good. Now we already know that we can write, so in the coordinate basis we can write x as x mu del by del x mu. Okay, so that let's write it in using these components. So let's write x as x mu del by del x mu in the chart x mu. Okay, and y as, I have to use a different index here, y nu del by del x nu acting on f, right? This is a new function. It's just the product, the pointwise product of two functions, right? This is a function and this guy is a function. The pointwise product of two functions is again a new function. And now we are writing y using this coordinate basis as y nu del x nu, and it's going to act on x mu del by del x mu f, right? Good. So now we know that the derivative operator obeys the Leibniz rule, and hence we can decompose it, because these are two functions and this derivative operator will be acting on the product of these two functions using Leibniz rule. So this is going to be x mu del y nu del x mu, and then I have this function del f by del x nu, and following which I have x mu and then y nu, and then del square f del x mu del x nu, and then I have here y nu del x mu del x nu del f by del x mu, and then I have a minus sign here, y nu x mu, big X mu of course, del square f by del x nu del x mu. Okay, Now we know that using our basic knowledge of multivariable calculus, we know that they cancel each other, right? This cancels against this. And finally, what we have here, so the first term can be rewritten by exchanging the indices, right? So these are dumb indices, so doesn't matter if I replace mu with mu and mu with mu, doesn't matter because they are dumb indices. So let us do it. So I can write it as x nu del y mu del small x mu and del f by del small x mu, right? By using the dumb indices, by changing the dumb indices, and I leave as nu and mu are in the second summand. Y nu del x mu del x nu and del f by del x mu. So from here we see that we just factor out del f by del x mu to obtain here x nu del y nu by del x nu minus y nu del x mu by del x nu, right? And well, we expect this guy to be, you know, in the coordinate basis to be x, y, mu, okay, del by del x mu acting on f, right? Since this is something that we expect to be a vector field. So if this is the case, then we see that we have del f by del x mu on both sides. So the components of the commutator should be this one, right? So let me erase this part. So we expect the components of the commutator of the two vector fields in the coordinate basis to be the following object: x nu del y nu by del x nu minus y nu del x mu by del x mu. Okay, so thus we see that the components of the commutator of two vector fields in the coordinate basis should be written like this. Okay, good. Now there is a small remark here which tells us that, since see that when we have a vector field like del by del x mu, then if I write it out using the coordinate basis, then the coefficients after we write it out in the coordinate basis should be just constant numbers, right? The coefficient here is 1. And same is true for del by del y, del by del x nu, right? So So all these components for these vector fields are constant numbers, which is just 1. Okay, so when we derive them with respect to these coordinates, local coordinates, we are going to have 0. So we have the commutator of these coordinate vector fields to be simply 0. Okay, now we are going to introduce a very important tensor field called the metric tensor field. Okay, let me erase everything. The metric tensor, or the metric tensor field, that we are going to introduce now. The metric tensor. Okay. Now here is the motivation. Consider a curve in R3. Consider a curve in R3. Okay, this curve. Okay, so we get a vector at each time where this time parameter takes its value between a and b, and as t takes its value between e and b, these vectors trace out a curve in R3. Okay, so the length of this curve, as we know from our knowledge of basic knowledge of calculus, the length of this curve is given by the integral, right? From a to b, the two limit points of the parametric values. Okay, and integral over t, and we are going to take the norm of this velocity vector, right? Or the tangent vectors at each point of the curve, and then integrate it from a to b. That's how we get the length of the curve. Okay, so in other words, this is nothing. We can rewrite this known as as an inner product with the help of inner product, right? Or the dot product between two vectors, right? Good. So motivated by this scenario, we now define G, a metric tensor field of type 0, 2. So G is our metric tensor field. Here we are going to denote this metric tensor field by G. It's of type 0, 2. Okay. So in general, we discussed. So in the beginning of this lecture, we opened our discussion with an R, S tensor field, right? So now we are going to consider 0, 2 tensor field. So it's so the metric tensor field is a tensor field of type 0, 2, of type 0, 2. So at each point P of M, this metric tensor field is going to define a map G restricted to P, which is nothing but just a tensor, right? So when I restrict this metric tensor field to the point P, it's just a tensor. And this tensor is a multilinear map that we discussed in the previous lecture, that every tensor can be thought of as a multilinear map, and since it's of type 0, 2, it is considered to be a map from TPM cross TPM to R, right? So use your knowledge of lecture 3. It has the following properties. We expect this metric tensor field to have the following properties. It has the following properties. 1. Symmetry. For any two tangent vectors, x at P and y at P in the tangent space on the manifold TPN, right? G at P acting on these two tangent vectors at P should be the same as G at P, y at P, x at P. Doesn't depend on the order how we put them. Okay, this is what we mean by symmetry. Secondly, we expect it to be non-degenerate. What do we mean by that? Non-degeneracy. It needs to be satisfied at the same time. If G restricted at P, x at P, y at P is 0 for all y at P in the tangent space TPM. If this is the case, then we must have x at P to be identically 0. Okay. This is what we mean by non-degenerate. The metric tensor field to be non-degenerate. Okay. Okay. So now, in the literature, you will see in many books of GR or in books of differential geometry that G at P, x at P, y at P, which is just a number, right? This guy is supposed to be a number, and this number is written by this inner product notation, or sometimes as a dot product between these two tangent vectors. In literature, you will see this in various notations, okay, but they are the same. Okay. So again, there is another remark on notation. Let me put it down. A remark on notation. So in the chart, if you use the chart x mu, okay, in this chart we can, so from our knowledge of lecture 3, we can always write a tensor, right? It's a 0, 2 type tensor, and this can be expanded in basis elements in the, well, you see that so in this case the vector field is of dimension n squared, right, where n is the dimension of the underlying manifold. So the dimension of these vector spaces where these guys belong, well, the dimension of these vector spaces is n squared, okay, and right, and so there are n square basis elements, okay, and they can, so each of these guys can be written down as a linear combination of this n square basis elements, and this is what we are doing now. G mu nu at P and dx mu at P tensor dx mu at P. Okay, so so mu varies from 0 to n minus 1, and nu also varies from 0 to n minus 1. So there are n square such combinations. Okay. That there are n times n such combinations, or n square such combinations. Okay, so there are n square basis elements in this vector space, and this is the basis expansion of this metric tensor at the point P, which is nothing but a linear combination of those n square basis elements in this vector space of n square, in this vector space of dimension n squared. Okay, good. So now G as a 0, 2 tensor field can also be written as, now I'm just writing G, not G at P. G at P is a 0, 2 tensor, and G is a 0, 2 tensor field, and we can conveniently write it as this, right? G mu nu dx mu tensor dx mu. So this is what we wanted to remark about notation. So the metric tensor is conveniently written like this. Okay. Now, remember, so whenever we have a manifold M, so if we take the local vector fields on this manifold, and we write down the space of vector fields on this manifold as with this notation. Okay, so it is the space of vector fields on M, or the local vector fields to be more precise on M, and x, y, these are vector fields on M. So in that sense, x and y, they belong to this space, the space of vector fields on M. Okay, so now if x and y are two such vector fields, then g x comma y is a map, right? This is what we defined in the beginning of this lecture. So this is how, so out of a tensor field, we define a map like this, right? And this guy at P is supposed to be a number, right? And this number is nothing but G at P acting on X at P, Y at P. Okay. And we have studied in lecture 3 that if you use this notation, that if we write G mu nu at P dx mu at P tensor dx nu at P, and this guy is going to act on this pair of tangent vectors, right? And well, right? These tangent vectors are nothing but, so if I write it in terms of components, so then this can be written down as x sigma at P del by del x sigma at P, and this can be written down. So I choose a different index like y row at p and del by del x row restricted to p. Okay, so now their action on, so the action of the covectors on the corresponding tangent vectors, the way we define it in the third lecture, we are going to have g mu nu at p, and then we have x sigma at p, then we have y rho at p, and this action is going to give us a Kronecker delta mu sigma, and this action is going to give us a Kronecker delta mu rho. Okay, so finally what we have is g mu nu at p, and see that so because of the presence of this Kronecker delta, all the terms except for the mu will go away. So we have x mu at p, and then you have y mu at p. Okay, so we just have seen that this number g of x comma y at p is nothing but g mu nu at p, x mu at p, and y nu at p. It's a number, right? See that mu is contracted against this mu, and mu is contracted against this mu, and according to physicists, this is a number. Okay, so we have a number. Good. All right. So let me erase everything. So now important thing to note here is that the components of this guy, right? We have just seen that g x y at p is going to be this number, right? G mu p, x mu at p, and y mu at p, right? So these numbers, the components of this tensor, right, form a symmetric matrix because of the property of symmetry of metric tensor, right? It forms a symmetric matrix, and such a matrix can be diagonalized following an appropriate choice of basis vectors of the corresponding tensor product vector spaces. So we can choose appropriate basis vectors or basis elements to diagonalize this symmetric matrix. Okay. So non-degeneracy implies that none of the diagonal elements after diagonalization will be zero. So if you focus on the property of the metric tensor field, you will see that non-degeneracy implies that none of the diagonal elements after diagonalization of that symmetric matrix will be zero. So no eigenvalues will be zero. So in an orthonormal basis, the diagonal elements reduce to plus minus 1. Okay. So if we choose an appropriate orthonormal basis for the respective tensor product vector spaces where these metric tensor fields lie, where these metric tensors lie, the diagonal elements will reduce to plus minus 1. Okay, now there is an important note here. Important note. In differential geometry, one is interested in Riemannian matrix. Okay, one is interested in Riemannian matrix. Okay, which means that these when you do this diagonalization thing in differential geometry, when in the context of Riemannian matrix, you get all the unity to be positive. Okay, so there is no negative one, which in other words, we say that the signature of the metric is plus 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 plus. All the one comes with a positive sign, which means that all the diagonal elements are plus in the orthonormal basis, and hence G is also positive definite. So this is relaxed in general relativity, or pseudo, or Lorentzian case, okay, or pseudo Riemannian matrix case. In differential geometry, we add this extra property that G is required to be positive definite. That has been relaxed in the context of general relativity. Okay, so in GR, we are rather interested in Lorentzian matrix. That is, those with signature minus plus 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 plus. So the first one coming with a minus sign. Okay, the first one comes with a minus sign in the required orthonormal basis. But in differential geometry, all the one comes with a positive sign. Right? All the one comes with a positive sign. Okay. Okay, now we give the definition. And by the way, it is important to note here that the signature of the metric is independent of the choice of the basis of the corresponding tensor product vector space. So we are saying that we are diagonalizing this symmetric matrix with respect to an orthonormal basis. So it doesn't depend on the choice of the basis. So this signature plus minus 1, they don't depend on the choice of our orthonormal basis. Okay, I think I take a break here, and in the second segment we'll carry on with the definition of the Riemannian or Lorentzian manifold. Thank you for attending the first segment.